So yeah, diffusion models are a very new idea in deep learning. You'll hear more about that. And the idea that we can actually forecast the weather with machine learning accurately is about a year old. So I figured I'd victimize two other people to try out this new method on this topic. And diffusion models are really cool because you can also do ensembles with them. And in every meeting I have with like DeepMind and NVIDIA and all these big companies, they have essentially two topics they want to talk about, and one of them is ensemble. So with that, I give the stage.
Hello, everyone. I'm Mohit, and I'll be presenting together with Jonathan about the diffusion models on WeatherBench. We would like to thank Jesper, Florian, and Matt who helped us throughout the entire project. We would also like to thank Athena and Esperanza for taking care of all the organizational details. And yeah, so I'll start with the diffusion models. So in last 6 months or so, we have seen many examples of diffusion model in the form of stable diffusion or DALI, where we have some conditioning information. It could be in the form of text or images, and then we again generate images. For an example, this conditioning information could be something like this: a cute image that I can use to illustrate a presentation on machine learning for weather predictions. And then you get cute images like this. But we are not just interested in the cute images. So in our midterm, we explained the diffusion models in detail. And here we will just give a very high level overview. So a diffusion model takes some noise as an input together with some conditioning information. For example, in our case, it's the current weather, and it helps us produce some predictions in the future time steps. We are using WeatherBench dataset to train our diffusion models. WeatherBench dataset include ERA5 reanalysis dataset that we already saw in the introduction lecture as well. And we are using two relatively coarser resolutions, which combines of 32 cross 64 and 64 cross 128 pixels. The time steps that we are using is the temporal resolution of the dataset that we are using is 6 hours. And generally, in most of the cases, we use previous 3 time steps of data to predict the future. And for our case, the training set consisted of the data from the year 1979 to 2015. The validation set was for the year 2016, and the test set was for the year 2017 and 2018. The data set consists of many different variables like geopotential height, temperature, humidity, and wind at multiple pressure levels. We select a subsample of them, and since we have multiple variables at multiple pressure levels, the data set quickly becomes quite large, and it took roughly like from 12 hours to 1 day to train each of our model on 800 GPUs, depending upon the complexity of the model. Today, we have our diffusion models in 2 settings. One is iterative, in the setting of iterative prediction, and the second one is direct prediction. In iterative predictions, we feed an input at a time step and then predict the next time steps based on the output of the previous time steps. While in the direct prediction, we start from a time step and directly predict the time step we are interested in. Both the methods, iterative prediction and direct predictions, has their own advantages and disadvantages. For example, when we do an iterative prediction, we get the evolution of the dynamics throughout the entire time, while when we do the direct prediction, we reduce the chances of errors accumulating from one model to the other model. The other thing about iterative prediction is we also need to produce at each time steps all the input variables for the next time steps. So I'll quickly go into the results. So what you see on the leftmost panel is the target, which is geopotential at 500 hectopascal. And what you see in the middle panel is the predictions with an increasing lead time. And the rightmost panel shows the difference between the target and the prediction. What we very clearly see that our error or the difference between the two is increasing with lead time. At the same time, the errors are larger in the high latitudes compared to the middle latitudes. But this is just one specific variable. So we did this again for the temperature at 850 hectopascals. Here also we see that the difference between the target and the prediction keeps on increasing with time. Though the errors are larger, again, on the higher latitudes, the difference between the errors between mid and the higher latitudes is less compared to the geopotential at 500 hectopascals. So now we have seen that we have this qualitative results or good images, but we need to do more quantitative analysis or compared with different baselines. For this, the first wave of deep learning methods for weather prediction came with the WeatherBench, with the release of the WeatherBench datasets, and we had different models starting maybe say roughly around 4 to 5 years back. And now, as Jesper already mentioned, like there are many different models coming up from the industry, and some of them, like each of them uses a different kind of network, like adaptive Fourier neural operators or vision transformers, and or the graph networks. But what we don't see there is the diffusion model. And one of the aim of this project was to really explore diffusion models to do to see how well they do compared to the different models. And we also see that for most of these models which came up in last 6 months or a year, they competed quite well with the numerical weather predictions, even outperforming them in some of the metrics. And thus, yeah, the idea was to know where does the diffusion model stands in general, or how well does it do. And from here, maybe Jonathan will tell you more about the results.
Thanks. So I have to start with a slightly disappointing message. So we were not quite able to keep up with Google and NVIDIA. And so we show in this plot, we will show like roughly the performance that we had. And what we plot here is actually like the root mean squared error. And we plot this like for averaged over the entire globe, weighted by area. And we plot this as a function of the lead time. So how many days we want to predict into the future. And what we show this is the root mean squared error for the geopotential height, which, like, in case somebody doesn't know, it's just like a standard meteorological variable and tells something about like pressure systems, for example. Okay, so what everybody's trying to beat is the ECMWF's operational model, and this is this dotted line here. So the best entry in WeatherBench was before this NVIDIA era, was still quite a bit worse than this. And it turns out like our diffusion model, at least with our implementation, is still a bit worse than this. But on the WeatherBench dataset, we are somewhere in the middle. So we're beating a lot of the baselines they have. We're also beating some of the machine learning models, but we are not competitive with the very best model. So the question is then, like, why would you even want to use diffusion models? Are there reasons you would even use diffusion models if the overall performance in terms of root mean squared error is a bit worse than for other models? And as Jesper already said, one thing that's really cool about diffusion models is that you can create ensembles. You can do this the following way. So if you remember the introductory example by Mohit, we had like one conditioning information, and then we created like a bunch of images, and we can do the same thing here. So we can start with one initial weather time step, and then we can create like a bunch of different possible realizations in the future. So for example, we could predict 3 days ahead in time, and then have a bunch of ensemble members, and then we can have a nice probabilistic analysis. And so it's also somewhat related to the talk we had earlier on like the fire forecasting. We also created ensemble methods. Okay, so before I show some results, I think it's worth like studying what actually like what are we aiming for. So what is a good ensemble, and what is like a good ensemble spread? So conceptually, let's imagine it like this. Let's say, okay, we choose randomly some pixel, and we choose a random value, for example, geopotential. And we start at a given time point, and then we do a prediction, and we end up with like a bunch of realizations from the ensemble predictions. And this ensemble then has a spread that might be like the standard deviation that I call sigma here. And then let's assume we have a true observed value that lies here. I think in this case, like most of you would agree with me that the ensemble is like a bit too narrow, because like the true value is even outside the range of all the ensemble members. But what we also don't want is like the opposite. So it would also not be great if every two observations would lie perfectly in the center and the spread would be very large, because then, of course, the ensemble could just decrease its spread and we would have more precise information. So actually, there's a sweet spot between these two, and this is precisely the case when this root mean squared error between the ensemble members and the true value equals the spread of the ensemble. And this is exactly the metric that we'll use in the following slide. So let's go step by step. The first thing that we computed is the root mean squared error between the true value and the ensemble members. In this case, it's an ensemble with 5 members, so it's just a very small conceptual example. And we can see that this also confirms with what Mohit showed earlier, that the errors grow the largest over high latitudes, and we can see that the root mean squared error is also largest in these regions. So now the ensemble standard deviation also follows this trend. So in general, the ensemble spread is largest in the region where also root mean squared error is largest. But as you can see, the colors are quite a bit fainter here, which means that the overall values are also smaller. And to quantify this, you can take like the ratio of the two of them and just divide root mean squared error by the standard deviation. And if you remember from the last slide, this ratio, so these two things should be equal, which means that the ratio should be 1. So ideally, this map would lay somewhere close to 1, but actually what we observed is that we are somewhere between 1.5 and maybe like 3.5. So the overall conclusion that we can take from this is that, yes, we get an ensemble spread, but at least in our case, the ensemble is like not spread out enough, or the prediction didn't work good enough, which is kind of like an analysis. Okay. We also tested this ensemble aspect in a case study. And what we looked into here is like a heat wave that happened in 2018, so in a test set of our data set. And it was a heat wave in Scandinavia that took place from somewhat mid-July until the beginning of August. And yeah, we focus on the region that we highlight here in red. And the values that I will show later are just like average values over this region. And we focus only on the temperatures around noon. And yeah, what's shown is just the temperature anomaly. So red means that it's hotter than like in the usual, like in this usual day of year. Okay, so if you have a heat wave, it could be nice to be able to predict this ahead. So as an experiment, we went to like a very large prediction lead time. In our case, this would be something like 5 days. And then we would start from, for example, for this point here, we would create a prediction from the 5th of July. And then you can, we would, for example, get this realization of the machine learning model. And you can see, okay, there's quite some error between the machine learning model and what actually happens. And then you can continue with this process and do this like for every time step in the model. And as you can see, so the nice thing about diffusion models is that they don't only get a single realization, so you get like a spread. And what I show you is just like all the ensemble members and taking the minimum and taking the maximum of the ensembles. And yeah, if I go through this to the end of the heat wave, you can see, first of all, this doesn't quite match. So at least for the very long lead time that we chose, our model didn't manage to predict the heat wave nicely. But overall, we can see that the rough shape is somewhat represented. And I think we can still convince you that like having this ensemble spread is better than not having the ensemble spread. All right. And then like a third analysis that is something that might turn out like or emphasize the value of diffusion models is the fact that many of the machine learning models, they tend to produce very smooth predictions. And so I think I want to give credit to Mariana here, who shared the code to produce this figure. And so what we are going to plot here is basically a spectral variance, which says like how much variation is there on a specific scale. And on the bottom, we have the wave number, and this ranges from like large scale structures on the left to very small scale structures on the right. Okay, and this is what we actually get. So what you see here is in black, what is actually the observations. We see in green in dashed green what our ensemble does. And in blue, we have one baseline. This is typically used in like image analysis. So it's a unit model. I think like if you do like computational like machine learning, you've probably heard of this model before. And so also I have to say that the unit here was better in overall predictions than our diffusion model, but you can still see like in this metric, it's not quite as good. You can especially see this in this region here. So you can see the unit curve is quite a bit lower than the diffusion model curve and also the target curve. And this means that there's too little variability in this frequency range. And this basically means that there's like these structures are smoothed out too much. So we can see that at least in this aspect, our diffusion model really paid off, like using it paid off. Okay, then I think I can already come to the conclusions. So what we did was largely exploratory work. So nobody had tried this diffusion models ever before. And it's also, you have to keep in mind that we're competing with like people like Google and NVIDIA on this topic. And yeah, so the main challenges that we faced were just like the large dataset amounts. And if you have this diffusion models, there's just a super large design space. It already starts with the variable choices you make in the beginning, because error 5 has a lot of variables and you have to decide which ones do I take, which ones do I leave out. You can implement a diffusion model in like 10 different ways, and then there's modifications you can make, and just making the right choices in this design choices in this design space is not easy. So to summarize the results, in terms of just root mean squared error, our results are not quite competitive with the large deep learning models, but I think people who are interested in this topic further, they might still look into this because of the nice aspects that the method has, which is like the non-smoothing nature and the ensemble uncertainty that we get from it. Yeah, I forgot to mention the code is of course available on GitHub, and if you want to play around with this, try it out, have a go. Yeah. One way to improve the results even further might be including latent diffusion, which is also what these online image generators use. It's just one step more complicated, and we didn't manage to implement this in time. But we did talk with an author of a paper that implemented diffusion models, and he said it's actually something that helps him quite a lot. So I think this is really a promising direction.